Welcome back to Statistical Methods. This is Week 8, Lecture 1, where I'll be covering dependent and independent samples t-tests. So I'll be continuing to talk about dependent samples t-tests and beginning to introduce independent samples t-tests. Just some announcements before we get fully into the lecture. Quiz 3 goes live on Monday, October 19th, and this will be due Friday, October 23rd at 11:59 p.m. And Quiz 3 will cover weeks 6 through 8 material and study the Kahoot question sets as usual to do well on this quiz. And the quiz will be open notes, slides, Kahoot, and textbook as usual. And then one other thing to keep in mind is that homework 4 will go live also on Monday, October 19th, and this will be due Monday, October 26th at 11:59 p.m. So a little recap. So recall that a dependent samples t-test is used to compare pairs of scores taken from the same individuals. So this is a basic example of a within subjects design where the independent variable is manipulated within a single group of participants as opposed to multiple groups. And a dependent samples t-test is essentially conducted in the same way as a one sample t-test, but your sample mean and S of m now refer to different scores. The mean is compared to a test value of 0 as opposed to a mu of m based on some known mu or population mean. Now let's break each of these components down in more detail. So remember that with a dependent samples t-test, we are interested in comparing pairs of scores taken from the same individuals, asking whether they are significantly different from one another or not. So how do we quantify how different scores are on average? Well, we do that by computing simple difference scores. So measurement 2 minus measurement 1, and then computing their sample mean. Now this mean tells us how much did scores change on average from one measurement to the next. So previously we needed to know the null population mean to figure out the mean of our comparison distribution, U of m, which was a distribution of sample means taken from a hypothetical population where there is no effect, or in other words, the null hypothesis is true. Now, what will the mean of our null comparison distribution be for a dependent samples t-test? Well, the null hypothesis in this case is that there is no difference between the two measurements, so from pre to post, or time 1 to time 2. Thus, we would expect the mean of different scores to be 0. So a dependent samples t-test is conducted by comparing our observed sample mean of different scores to a hypothetical distribution of mean difference scores centered on 0, indicating a lack of difference between our two measurements. So here's an example. A legal psychologist wants to test the hypothesis that group decision-making contexts tend to make mock jurors more punitive. So he recruits n equals 18 participants who are first individually presented with evidence in a case and then provide their certainty of the defendant's guilt on a 1 definitely not guilty to 7 definitely guilty scale. And that's the pre-guilt measure. And then afterwards, participants join together in groups and are allowed to freely deliberate and discuss evidence for 30 minutes. And then afterwards, participants then answer the same guilt question again. So that's the post-guilt measure. So here is your time 1 measurement, and here is your time 2 measurement. Notice that these are the same participants. They're just taking these two scales twice. So the researcher ends up with data that looks like this. In the first column, you have your subject ID. In column B, you have your pre-guilt score, and in column C, you have your post-guilt score. So again, this pre-guilt score was taken before participants were allowed to deliberate in groups, and this post-guilt score was taken after they deliberated in groups. Now, this research will compute difference scores, representing how group deliberation changed people's opinions on the defendant's guilt. And they'll do this by subtracting what's in column B from what's in column C. So subtracting pre-guilt scores from post-guilt scores. Now the sample mean of different scores in this case ends up being m equals plus 0.8, indicating that certainty of the defendant's guilt increased from pre to post deliberation. But is this increase statistically significant? In other words, how probable is it that our sample of different scores comes from a population of different scores centered on a mean equals 0? Now let's work through the 5 steps of null hypothesis significance testing to find out. So step 1 is to restate the question as a research hypothesis and a null hypothesis about the populations. So a research hypothesis is that mock jurors will become more certain of the defendant's guilt after group deliberation. So mu1 will be higher than mu2. And the null hypothesis is that our mock jurors will not become more certain of the defendant's guilt after group deliberation. So mu1 will be less than or equal to mu2. Step 2 is to determine the characteristics of the comparison distribution. So we know that we want to use a test value of mu of m equals 0, indicative of a lack of change from pre to post guilt scores. And we will estimate the variance of the population of different scores from our sample of different scores, just as we did with a one sample t-test. So imagine that we have a sum of squares of 50 and degrees of freedom of 17. So keep in mind your degrees of freedom is still n minus 1, just like a one sample t-test. And these values here were calculated based on our sample difference scores. So to get our unbiased estimation of population variance, we subtract, or rather we divide the sum of squares by the degrees of freedom. So in this case, sum of squares is 50 divided by 17 degrees of freedom. So s squared is 2.94. And to find s, the unbiased estimate of population standard deviation, we take the square root of our variance, which is 1.71. Now to find the standard error of the mean, we divide s by radical n. So 1.71 divided by radical 18, and our standard error of the mean here is 0.40. Thus our comparison distribution has a mean of 0 and a standard error of 0.4. Because we are working with an estimated as opposed to known population variance, this will be a t-distribution with 17 degrees of freedom. And that leads us to step 3, which is determining the cutoff sample score on the comparison distribution at which the null hypothesis should be rejected. And let's say this researcher wants to use the standard p equals 0.05 cutoff with a one-tailed test and 17 degrees of freedom. So if we're using our t-table, we look in that 0.05 column, look down to 17 degrees of freedom, and this is the t-score we would need to have or higher in order to reject our null hypothesis. If we use the Shiny app, we adjust probability, enter 0.05, and 17 degrees of freedom, one-tailed upper, and we get that 1.73961 cutoff score. Now step 4 is to determine your sample score on the comparison distribution. So this is exactly the same as a one sample t-test, but now that we know, but now all of these statistics refer to different scores. For example, a sample mean of different scores, mean and standard error of a sampling distribution of different scores. So here, t, the t value equals our mean of different scores that we observe from our sample, minus the comparison distribution's mean, which is 0, divided by that standard error of the mean. So if we plug in our values here, our mean difference score was 0.8 minus 0, the comparison mean of the null hypothesis difference scores, divided by the standard error of 0.4, which yields a t of 2. So step 5, we determine whether or not we reject the null hypothesis. So is our t-score more extreme than the cutoff score? Well, our sample's t-score is 2, the cutoff score is 1.74. So yes, our t-value is more extreme than the cutoff score, so we reject the null. And we can use the Shiny app to figure out what p-value is associated with a t-score of 2, assuming 17 degrees of freedom and a one-tailed test. And since our p-value is less than 0.05, we reject the null. So an effect size that we can report for the dependent samples t-test is a type of Cohen's d, a standardized mean difference. So d equals our mean difference score minus 0 divided by our estimate of the population standard deviation. Now this effect size tells us how many standard deviations, in terms of the estimate of the population standard deviation, from 0 is your sample mean of difference scores. Thus, it's an estimate of the magnitude of the effect free from sample size. So to calculate this, we would need our mean of 0.8 minus 0 divided by 1.71, which equals 0.47. So the interpretation is that our sample's mean difference score was 0.47 standard deviations away from 0. So that gives us an estimate of how large the effect that we observed here is. So that is dependent samples t-tests, and now I'll move on to independent samples t-tests. Now, this might not be chapter 8 in the current version of the textbook. It might be chapter 9. So previously we learned how to test whether two dependent sample means taken from the same group of participants differed from one another. And that was a within subjects design. But now we'll learn how to test whether two independent sample means taken from two separate groups of participants differ from one another. And this is a between subjects design. So here's an example. An evolutionary psychologist hypothesizes that men should express more concern than women about whether offspring resembles them. So the psychologist obtains a sample of 50 adult men and 50 adult women from the general population, has them come into the lab, and then uses face morphing software to create photos of babies that resemble or do not resemble them. And participants were shown these images and asked how willing they would be to spend time taking care of the baby in the photograph on a 1 through 7 scale. And the researchers' hypothesis is that men will express greater willingness than women to spend time with the babies that resemble them, as opposed to babies in general. And to test this hypothesis, the researcher needs to compare sample means for two independent populations, both with unknown mean and unknown variance, so the men and women's willingness ratings. So carrying out this hypothesis test using difference scores and conducting a dependent samples t-test wouldn't make sense, right? Because how would we create pairs when scores come from different samples of people? Our result would rely on arbitrary decisions about how to match up participants. Instead, this researcher will need to conduct an independent samples t-test, asking whether the means from our two separate samples are significantly different from one another. So remember that our null comparison distribution needs to match the characteristics of the test statistic we're calculating. For a one sample t-test, we compare our sample t based on the sample mean to a sampling distribution of means. In a dependent samples t-test, we compare our sample t based on a mean difference score to a sampling distribution of mean difference scores. Here, we will want to calculate a t-score representing the difference between two independent sample means. Thus, our null comparison distribution now has to be made up of differences between sample means. So here's how you create this new sampling distribution. Step 1, repeatedly sample from population 1, which is men, creating a sampling distribution of means for this population. 2, repeatedly sample from population 2, this population of women, creating a sampling distribution of means for this population. Step 3, randomly sample two means, one from sampling distribution 1 and one from sampling distribution 2. Subtract one from the other, and then plot this difference. And then you repeat steps 3 and 4 over and over and over. The result is our desired comparison distribution, a distribution of differences between means. So we have our two populations. We have our distribution of means, and then we have our distribution of differences between these two means. And we do this over and over again. So as with a dependent samples t-test, we only know the information that comes from our sample, or in this case, our two samples. We don't know mu, the population mean, and we don't know sigma, the population standard deviation, for either of our populations of interest. So what do? Like before, we use logic to figure out what the mean of the null comparison distribution will be. And B, we estimate its variability based on sample data. Now, step B will require a few additional calculations to get from our raw sample variability sum of squares to the variance and standard deviation of the distribution of differences between means. First, what will be the mean of this comparison distribution, or the distribution of differences between means? Well, it will be 0. Why? So although these tests answer different questions, the logic here is similar to a dependent samples t-test. We don't directly know mu for either population of interest. What we do know is that if the null hypothesis is true, these two populations will have equal means. Thus, the sampling distribution of means taken from these populations will also have equal means. Taking this one step further, the mu of m of the distribution of differences between means should be 0 if the null hypothesis is true. Now, a key assumption of the independent samples t-test is that the two populations your samples come from have the same variance, whether or not their means differ. So this assumption is called heterogeneity of variance. Well, this assumption is actually called homogeneity of variance. We'll start by calculating s squared and estimating sigma squared for each of our two groups the same way that we did previously. S squared equals the sum of squares divided by degrees of freedom. We'll then have two separate estimates, one from each sample for what we assume is the same number, the true underlying population variance. These estimates won't usually be exactly the same, so we get the best estimate that we can by averaging these two estimates together to get a pooled estimate of the population variance. However, as these two samples may not have the same number of participants and thus don't contribute the same amount of information, we'll want to use a weighted average. In other words, an average estimate of the underlying population variance that is adjusted according to the degrees of freedom in each sample estimate. So to find this weighted average, you figure out what proportion of the total degrees of freedom each group contributes. You multiply that proportion by the estimate of the population variance from that group, and then you sum these two weighted variance estimates together. So df1 and df2 is the df from each individual group, so the group of men and the group of women, and that will be n minus 1, the number of men minus 1 and the number of women minus 1. And then df total is equivalent to your total sample size minus 2. So the number of men you have, the number of women you had added together, minus 2. And s squared 1 and s squared 2 is your estimated variance from each sample. So that's sum of squares divided by degrees of freedom. And that's all I have for this week, but we'll go into more detail about independent samples t-tests next week. Thank you.